Meter is another unit on the International System of Units, which is very important because it measures length. And the way that we define the meter is being varied along the history. We have done all kinds of interesting definitions. And of course, once you do the definition, you have to do the realization. So the definition passed to many different concepts, like the distance between two cities. In this case, it was in 1793, and the distance between Dunkerque and Montjuic in Spain was a number of meters. So if we are able to measure this distance between these two cities, we could get the meter by getting a fraction of this. Okay. Of course, this is very hard to realize, but people has realized that. Once they realized that, they came with the artifact, the bar of platinum that is being kept for a long time as the definition of the meter. Now, light is an important quantity, and it is a very good way of measuring, because if you are looking for some quantity that's easy to reproduce and is always constant, light seems to be a good one. And the light emitted by some elements, it seems to be even better. So they improve the measurements, right? This was the definition as a standard, and then they defined the meter in a different way. They said, well, if we can count the wavelength of light in a precise line, in a precise frequency, if we is finite and is fixed, if we can count how many wavelengths there is in a big length, we can define the meter. And then they defined that if we can consider the light from a krypton lamp, and then one of the transitions, a special red light emitted by them, and you measure a number which is 1,650,763.73 wavelengths. This defines the meter. Now let me show you how it is, because the light is this wave, electromagnetic wave, and we have to count the ups and downs to be able to measure, to add and to end with the meter. Okay, so because it's hard to see this oscillation directly, when we see light propagating, it's very hard because it's a very small quantity and very, very fast. We're gonna do an analogous, so we're gonna use again the water cube to show how that can be realized, how the meter could be realized in terms of adding wavelength of light. So here is the cube. So here we have a water tank, and of course by producing a motion here, we can make portions of the water to go up and down, and this generate waves that can propagate in the water. Okay, so let's start by producing waves here. What you see is actually the up and down of the wave. Each bright part is a up of the wave. And of course it's propagating because the same way light propagates, the waves in the tank propagates. And the distance between these two bright spots, as you can see, is moving, but this distance is the wavelength of this specific wave. And what I have to do, if this was a lamp, a krypton lamp, I have to somehow add up these wavelengths. I have to add that huge number of those wavelengths and be able to form the meter. That's a definition that is nice, but it's hard too, because I have to find the special devices to count. Special devices to count are the interferometer. With the interferometer we can really count those, as well as we're going to demonstrate in the next step of this lecture. Anyway, this was the way that's defined. Of course, the wavelength depends very much on the frequency. If I increase the frequency, the wavelength decreases, and that's why I have to choose a specific frequency that in this case was the frequency of a specific atomic line of krypton as the definition. Okay, now, but then people realize that, oh, maybe there is a better way. We are able to measure time with high precision, and waves are propagating in a constant speed. As you see, if I'm gonna measure, you see, I have this frequency, so this produces a wave, and if I follow with my finger one of those waves, I see a speed. I can even measure this speed. I have here a chronometer, so I could measure the speed of this light. The chronometer is there. So I could come here and measure the time of this front propagating here, and if I do that, and if I measure that time, I know the length, I can measure the speed of light. If I increase the frequency, I decrease the wavelength, but if I measure again the speed of light, I'm gonna find the same thing. So if I measure for different frequency, which means a different wave now, different wavelength, the time that the wave propagated from here to here is the same, which means the speed is the same because I fixed the length. And then, you know, this is because in the case of a light, the velocity of the wave is constant. If the velocity of the wave is constant, maybe doesn't matter what light I use, I can define the meter as the distance that propagates, the light propagates in some fraction of second. And that's how comes the new definition of time. So the new definition of the meter is now based on the propagation of the light. So if we can know the velocity of the light, and we know how long I have to wait for the light to propagate for 1 meter, then I can define it that way. So the definition now, which is based on the propagation, let's make a demonstration here. So if we have the tank, we have the waves being propagating. So if we now have the light propagating and we know the speed, we can define, if I fix a precise, remember I measure the velocity of the light. So if I start one wave and follow the propagation, so if I measure the light propagating, this distance from the beginning to my fingers here, which is the distance that propagates that amount of time, I can define as time. And I can define as time because now the velocity of the wave, the velocity of the light in this case, is fixed, right? And then, based on this, comes the new definition of the length, which is basically the light, the distance that the light propagates in a interval of time. And this interval of time is very small because the light has a very high speed. The speed of light is about 300,000 kilometers per second. And then to define 1 meter, it has to be a very tiny time. But as we saw before, we can measure very well time. So if we can measure very well time in an interval of time, it's not a problem to measure this interval and define the length, which is the new meter. So as for the new definition of meter that's being adopted, you know, the proposed definition fixes the velocity of the light. So the velocity of the light is now defined as a very large number, which is 299,792,458 meters per second. And this is defined. You know, we don't need to measure anymore. That's a definition. It's defined that number. And once it's defined that number, if I see how much light will propagate in 1 over this speed, I have the definition of the meter, and that's what's being the implementation of the meter. Of course, measuring distance is small, big is always important, and then the next step is to show you the interferometer, which is something that allows to measure large and small distance with high precision. To demonstrate you how wonderful is the use of light to measure length, not only the definition of the meter as we saw, but also precise measurement of length. We brought here a light interferometer. You see that this interferometer has a light source, is a laser source that starts here. You can see the light. The light comes to a place that's divided in two. Part of the light comes to this arm, touch the mirror and return and come here. Another part comes to this another mirror, return and here, and then they combine. And because the light is this wave, they can add the oscillations, and they can have what we call a constructive interference, which is a maximum of light, or a destructive interference, which is a minimum of light. And because those are waves propagating here and here, when I move one of the arms, I can make maximums go to minimums and vice versa. And that's a wonderful way to measure length. Here we have a detector to start with. In this detector, we can see as the maximum of the light goes up and down as we move from a maximum to a minimum. And what we're going to do now is put the signal in this box, which is a kind of oscilloscope. And we'll show the signal going up and down. So let's look to the signal. And as you can see, of course, we are in some situation. But as I move one of the arm, you're going to see this going up and down, and each time I pass one wavelength of light, which is a tiny, it's less than a micron. We go from a maximum to a minimum. So let's take a look in the graph. As I move up and down, and you see the up and down, I'm going to do again. So as I move, you see the up and down and each up and down is one wavelength of movement of this arm. And because this is submicron, it means that counting the up and down, I can know precisely how much, what is the size of the distance that I travel. Let's do again and try to fix the plot in the screen so you can see what we're doing. So as you can see in the screen, as I move a little bit this arm, you can see from the top, we can see this arm moving. Você tem que mostrar o topo agora, que é para eu mostrar aqui. Isso. As I move this arm, here I have a screw, and as I move this arm, a quantity of distance, the mirror moves in some length, and each wavelength of light that I go, this light will go up and down and return back. So if you see again the signal that we have registered, so the signal you see is the total length. I just touch the screw, and by touching the screw I move many, I move many microns. If you count this up and down, you're going to know precisely how much I move. That is another way of seeing the movement. And this I'm going to do here by projecting in this piece of paper. As you can see from the top, you can see if we turn the lights down for a moment, right? Because those are what we call the interference fringes. And we have a collection of those fringes in the paper. And another way of measuring the distance is when I touch the screw here, you see that the fringes moves around. And when one maximum starts from its place and goes to the next, means that the screw moves one wavelength, which is nothing. For this case, it's 0.63 microns, or 6,300 angstroms. This is a very small distance, and this is very precise because I can measure a very tiny fraction of this. Interferometers are so precise to measure length that we can use it to measure very small amount on the atomic level. We have that precision. And that happens because the velocity of the light is constant in here. And any change on the addition in the interferometer is done because I'm moving one of the arm. Part of the light is advancing or being retarded, being delayed with respect to the other. And this makes the maximus and minimus adding or subtracting, and that's what I see here on the dark and bright part. Okay, so this is the interferometer. It's a wonderful device and is being used in many applications of precise measurement of length. Everything uses the light and uses, of course, the constancy of the velocity of the light.